Don't think of water as though it's just water. This has got all kinds of stuff in there. Tap water is basically like a rock smoothie.
I would go a step further, though, and say that a glass of water is actually just a glass of lava.
Right.
A cube of ice is made of a mineral, so it's a monomineralic rock. So melted ice is molten rock.
Therefore, everything you consume is lava. This episode is brought to you by Cancer Research UK.
Imagine this. Inside all of us, billions of cells follow millions of instructions written in microscopic code. And when a new cell grows, it copies those instructions, but the smallest error can lead cancer to develop.
Right, and this is the reason why there isn't a single cure for cancer, because, there are more than 200 different types. Each of them have got different distinct characteristics, different challenges, different mysteries. And that means that trying to cure cancer isn't like following a single path. It's like trying to map out an entire forest.
That's right. And Cancer Research UK is the world's largest charitable funder of cancer research. I mean, their work spans more than 20 countries, with over 4,000 scientists, doctors, and nurses pushing knowledge forward to save and improve lives worldwide.
Over the last 50 years, the work that this charity has done has helped to double cancer survival in the UK. And you have to think about that is more parents at the dinner table, right? That is more friends at their birthday parties. That is more people who are living longer, better lives.
For more information about Cancer Research UK, their research, breakthroughs, and how you can support them, visit cancerresearchuk.org/rest is science. Hello, and welcome to The Rest is Science. I am Michael Stevens.
And I'm Hannah Fry.
And today we're going to get a little bit splashy, a little bit wet. No, but we are going to talk about something that's wet. Water.
Hang on. Are you sure water's wet?
Actually, I'm not so sure.
This is quite a big question.
It's a very memed question. Is water wet? I have an opinion on it. Do you?
Go on, you tell me yours.
Okay, what I think is that one molecule of water, dry.
Okay.
Once there's more, it's soaking wet.
Soaking wet.
Yeah.
Well, hold on. We should say first about why this is a memed question, right? Because it's like water itself, the things that it touches are wet, but is the water itself wet?
Yes, that's right. Water makes things wet, but water on its own, would you call it wet? I would, because I think water can wet itself. Mm-hmm. Wetness is about intermolecular forces on water attracting themselves onto some other material.
Okay.
That other material, in my opinion, could be another water molecule. So just the surface tension between two water molecules means that they've wet each other.
So one water molecule, not wet, two or more.
Soaking
wet.
Yeah.
I'm just having a little sip of my drink here for those who are listening only. What are you drinking?
Oh, I'm drinking water.
I'm also drinking water, except that mine looks a lot like coffee.
Mine looks like coffee too, but it's still about 98% water.
Yeah.
In fact, everything we drink is basically just flavored water.
It is just basically flavored water, just different amounts of flavorings.
Yeah, we give them totally different names. We say, oh, that's coffee. If someone wanted water and I gave them this, I'd be 98% correct. It's basically a bullseye, and yet I'm wrong.
Are some drinks more watery than others, though? I mean, like Coca-Cola, for example, compared to, say, a seltzer.
Yeah. Seltzer is predominantly water, but it's got some carbon dioxide, maybe some minerals in there. Seltzer technically is only going to have the minerals that came from the taps, what is in the source. Club soda has a lot more minerals, but something like Coca-Cola, it's about 90% water.
Oh.
So that 10% makes a big difference because it's the difference between Coca-Cola, Pepsi, Dr. Pepper. But listen to this, Diet Coke is not 90% water.
Higher or lower?
99% water.
Is it?
It's basically just taking a bath.
Wow.
But it isn't though, is it? That 1% makes a huge difference. Now, the main reason is that you put sugar in Coca-Cola, there's a lot of sugar, grams and grams of it. But aspartame, it's so sweet. You just need a little sprinkling of it.
By volume, it's almost nothing.
By volume, it's almost nothing.
Wow.
So fruit juices, coffee and tea, alcoholic drinks like beer, That's also, it's like Coca-Cola. It's 90% water. But whiskeys, alcohols, spirits, they can be majority not water. So that's the thing I want to discuss today is like, what do we do with these edge cases? Because you can get 192 proof alcohol. That's 96% alcohol, which is a liquid at room temperature that's not water.
Yes, you're right. I think also the other edge cases right at the other end. I think it's probably important for us to say that tap water is basically like a rock smoothie, you know? Like, don't think of water as though it's just water. This has got all kinds of stuff in there. I mean, there's calcium, there's magnesium, there's sodium, there's potassium, there's oleums.
LA's water is very hard.
Is it?
It's got a lot of minerals in it compared to, say, the water in the Catskills, which provides water to New York City. In fact, there's a theory that it's that water that New York City gets from the Catskills that creates for them their unique, special, one-of-a-kind pizza doughs and bagels.
Makes it taste different.
It makes it taste different. And this isn't just some kind of guess. It really is true that those minerals affect how the gluten forms. It affects how the flour sticks together. And so there are companies that will either truck New York City tap water to your business, whether it be in Florida or Philadelphia. There are also companies that replicate New York City's tap water off-site by adding in minerals, having some kind of ionizing plant to make water that's like New York's so that you can recreate what they get for free.
Because this is the thing, right? Is that, you know, if water is just absorbing all of the minerals from the rock that it passes through, then actually you end up with different water being effectively like a really nice geological postcode of where it comes from.
Oh, sure, of course.
Right? Different pieces of water from around the world end up having these different compositions of the minerals. But what that means is that you can then reverse engineer it. So let's say that you're kind of drinking water your whole life. Those minerals, those isotopes as well, will end up embedding themselves within your body. So you can, if you find a body, for instance, right, somebody who's died, you can take a hair sample from them, go through and work out what water they were drinking when they were alive,
right,
in order to backtrace where they spent the majority of that time from. There's also, you can do this with whales as well. So whales, they have the ear bones of whales also will absorb the isotopes in the water as they're swimming. And different parts of the world, right? It's not just kind of fresh drinking water that has this postcode element. Also the oceans have different concentrations of minerals, different isotopes. So you can basically reverse engineer the migration patterns of a whale, work out where in the world it's been based on an analysis of the water that it was drinking and consuming and surrounded by. Actually, do whales drink water?
Well, they definitely take it in.
They take it in.
Yeah.
Drinking's probably a bit strong.
Oh, hey guys, I haven't had a drink in a while. All right, I'm good. But so they've got traces of the postcode of the water.
Exactly.
The characteristics of the water around them.
Exactly. You can do this with fossils as well, right? So whale fossils, you can go through and work out the point in history at which whales started their migration patterns.
How interesting.
Isn't that cool?
Yeah, so I could find a dead body and figure out if they were a tap water drinker or some kind of little Dasani sipper.
Well, I think if they're drinking Coca-Cola exclusively, it does make it slightly harder.
Tap water is a kind of mineral water. It's got minerals in it. That's the stuff that forms on your faucet. You know, over time, you get this scale that builds up, and that's just minerals that had been in the water. Hot water can dissolve a lot more minerals. So hot water will tend to form much more of a scale, and it also tastes a lot different. That's why when you make tea, you warm up cold water. You don't start with the hot water because it has a very different taste.
Well, okay, now you're talking with tea, because this isn't just making flour and dough, right? This is like you are directly tasting the minerals in the water. And if you speak to British people, they will tell you that if you're in Yorkshire, a cup of tea, so much more delicious than if you're in London. So you completely taste the difference in the water. But you get this in beer as well, right? Like the flavour in the water changes the taste of the beer. In fact, there's this British company, they're a beer subscription service. They're great guys. I like them a lot. The sponsorship team may or may not have been talking to them. Anyway, what they've done is they've gone to these really small breweries around the country and been like, hey, we want hundreds of thousands of cans of beer for our customers. And these small breweries have been like, whoa, I don't know, we're just not really able to fulfill that. So they've kind of stepped in to help them manufacture these numbers, but knowing that it's going to be really difficult to turn these small breweries to like up their manufacturing, what they've done is they're using this reionization plant in Buxton, where they go in to a small brewery, they work out the chemical composition of the water, the local water that they've been using to make their beer. They go to this reionization plant in Buxton and then tweak the water ever so
Buxton
subtle
to replicate the local water of the brewery. Right.
At which point they can then make these huge runs of beer.
And it makes a difference?
It makes a difference.
Well,
I mean, look, you find a Yorkshire tea drinker and they'll tell you it'll definitely make a difference.
Yeah, I mean, what's dissolved in your water makes a big difference. You mentioned earlier that a cup of water is like a rock smoothie, right? Because you've got rocks dissolved in it, magnesium and calcium. I would go a step further, though, and say that a glass of water is actually just a glass of lava.
Right.
Because I've talked about this before, and I bring it up whenever I can. Ice is a rock.
Sure.
Because, well, hold on. Ice is a mineral. Because a mineral is just a inorganic material that is solid and has a definite crystal structure, which ice does. Water is important for life, but it's inorganic, actually. It would exist here or whether there was life or not. And what that then means is that a cube of ice is made of a mineral, so it's a monomineralic rock. So melted ice is molten rock, lava. So water is lava.
I'm here for this.
And this is not a joke. Ice won the Mineral Cup back in 2015, I believe. Like some geologists all voted on their favorite mineral, and ice finally got the recognition it deserves.
Got the prize.
Yeah.
I mean, sure, I'm happy with that classification. If the rock people say it so, then I'm happy with it. They also move the same way. I mean, when lava gets spurted out of a volcano, it uses the way that it moves and behaves is exactly the same.
Like the fluid dynamics of lava.
The fluid dynamics of lava is the same as water at that stage. Yeah. Bit later on, when it cools down, then it changes.
Is it more like
slightly.
ice?
More like ice. There's a transition phase where it's more like toothpaste, where it needs a certain amount of shear forces in order for it to flow.
But that would be analogous to like slush, maybe?
Maybe, yeah. So now that we've established that ice is a mineral and that water is lava, I think we'll take a little break. Okay, welcome back from the break. What we've established is that water is lava, but also everything that you drink and eat is also water. Therefore, everything you consume is lava.
Pretty much. But let's talk more about the water on Earth and like how much there is and what form it's in. Because I think we in our day-to-day lives are very biased to think of water as this splashy puddle stuff. It's in lakes and rivers, but that is basically not what water is on Earth at all.
Go on.
Well, Earth has a lot of water, and it's famous for having a lot of water on the surface, but it's not water that we can just come up and drink because it's too salty. Most of Earth's water is way too salty. It would kill you to drink it.
Wait, when you say most, what are we talking here? What percentage of the water is?
I'll tell you. I'm going to have to pull up a chart because I want to get these numbers just right. So here's the deal. Earth has a lot of water, but of all that water on the entire planet, both on it and in it, only 2.5% is fresh, meaning
the rest is
not salty. And the rest is salty. But that 2.5% sounds small, but what we're looking for is even smaller because out of that 2.5%, almost 70% is frozen in glaciers and ice caps. So not accessible to just come up and sip. And then another 30% of that is groundwater, not up on the surface. So only 1.2% of the 2.5% that's fresh is on the surface, basically.
So wait, it's 1% of the 2.5%?
1% of the 2.5% is surface fresh water, but we're still not done. Because surface is being used really broadly here. That includes 3% of that 1% of the 2% is water in the atmosphere.
Right.
This is very small, but it's worth mentioning. 0.26% of that little sliver is locked inside living organisms.
Right.
Almost 4% of that little sliver is dampness in the soil. So I can't just go up and like slurp it up.
No.
I could stick some mud in my mouth and like
Try and suck on it.
We suck on it. But what we think of as fresh water, water from creeks and springs and rivers and in lakes, that is, I did the math here, 0.0072% of all the water on Earth.
Wow.
It is a tiny, minuscule fraction of the 1% of the 2.5% that's not salt water.
And if you think about it, all of the water that we effectively come into contact with, all of the water we're drinking, all the water we're showering with, all the water you putting in swimming pools, all of that is contained within that number.
0.0072%. Yeah. But it's the water that is the star of the human show. It's what we swim in. It's what we get out of the tap and that we drink and that we have right here. There is no salt water around us right now.
No, I'm not interested in the salt water. Thank you very much.
We're interested in such a narrow kind of water.
Of that tiny, tiny sliver, how much of that is in Coca-Cola? How much of that is tied up in...
how much is tied up in warehouses, in cans of soda and beer and brewed tea? Yeah, I don't know. I do know. Here's a fun fact. The entire volume of refrigerated space in the United States is equal to 2/3 the volume of Mount Everest.
Really?
I can't tell if that sounds small or big.
I think that sounds big. And the reason why I think it sounds big, I'm slightly obsessed with fridges.
Yeah.
Which I appreciate isn't a normal sentence, but they're wild. Like they are tricking the laws of thermodynamics.
Yeah, I know.
It's like you've managed to create this sort of tiny bubble in the universe where you have like sucked energy away. That's not what energy likes to do. Like it is miraculous that fridges have managed to work.
I know, and they do it so simply.
So simply.
They're just squirting around a fluid, and the fluid's properties are like, let's do it. Let's dump this heat out, keep your yogurt nice and cold.
I mean, also just think about before fridges existed, right? You could have lived, I don't know, for like most of the planet would never have experienced a cold drink, right?
I know.
Like, it's wild to me that we've had this thing for like 100 years or so, maybe a little bit more, 150 or so. I find fridges really, can we do a whole episode on fridges, please?
Yeah, we should. But where did all this water come from on Earth? How old is it? How long has it been around?
Well, it didn't get made on Earth, right? That's one thing that we know.
Water isn't produced naturally on Earth, right?
Correct. Which means it came here from space.
Alien water.
Alien water.
Yeah, I've heard that it probably came from like comets that crashed into a dry Earth and they left all this ice. It's hard to imagine, though, how many comets that would be. I guess that's why they call that the heavy bombardment period, when Earth was just getting smacked by these comets from way out beyond the solar system, made of ice, covered in ice, and they just delivered the oceans to us over time.
Do we know how old the water is then?
More than half of the water on Earth is older than the sun.
How do they know that?
Water can form naturally. It's an inorganic material. It's a molecule that can form all throughout the universe. And we know this because of a couple of things. One, when the sun formed, any water near the sun would have been obliterated into oxygen and hydrogen, just elemental or molecular forms. Wouldn't be water anymore. And so any of the water that remained would have had to have been further out, where it couldn't get destroyed by the sun forming. And then later, as the formation was complete, that water could fall down to Earth. And I think they've been able to test this by looking at the amount of heavy water in water on Earth and compare it to how water could have been formed more recently in the solar system.
And by heavy water...
Right, I mean water where the hydrogen atoms in it are deuterium, which is what, hydrogen with one neutron? Yeah.
Chubby hydrogen.
Chubby hydrogen. So it's still hydrogen because all you need to be a hydrogen atom is one proton with a little electron around. You get a little neutron in there, you're heavier, but you don't have any more protons. So your chemical properties are pretty similar. So it's still hydrogen, but it's called heavy. Now, I do want to give a shout out to tritium. If a second neutron comes along and joins that hydrogen nucleus, now it's got one proton and two neutrons, and it's super heavy. We call it tritium, and it's unstable. It's so chubby. It's about to like just barf stuff out. So it's radioactive. So tritium is extremely light radioactive gas, and it can be used. You might find it on watches. They fill parts of the dial with tritium gas inside little ampules covered in like some kind of phosphorus material. So when the radioactivity of the tritium hits the phosphorus, it glows, and they can make it glow for decades
because it's decaying.
Because it's radioactive,
consistent way.
And I think the particles that it decays out are mainly alpha particles,
which means they can't penetrate your skin.
They don't penetrate. They don't even penetrate the glass ampule.
Yeah,
that they only hit the phosphorus on the inside. But yeah, they won't go through even a sheet of paper. They won't go through your skin. It's much better than like what uranium does.
Shout out to tritium.
Shout out to tritium, yeah. But heavy water is water formed from deuterium and oxygen.
I should say though, actually, if you were drinking heavy water, different story.
Yeah, what happens?
Well, because then you've got this radioactivity going on inside you, and the particles cannot escape your body. So
but deuterium isn't radioactive.
No, but you don't want to be drinking tritium.
What do they call water made with tritium? Super heavy water. I don't think there's much.
No.
I think deuterium happens much more frequently in a context where water can be made, but I don't know. I know that if you drink a lot of heavy water, deuterium oxygen water, it can be bad over time. We're always drinking a little bit.
Yeah, there's
some deuterium, around. There's some heavy water in there.
You know what you also shouldn't be drinking is pure water.
Why not?
I mean, it is not good, because if you think about tap water as how it's got all of these minerals, in a rock basically dissolved inside of it. If you took away all of that,
so you only had water molecules,
H2O, nothing
H2O.
else. Right, now you have to remember that water is extremely good at dissolving things within it. So if that goes through your body, what that will do effectively is strip your body of all of the minerals that it naturally uses. And it can just be a very bad thing. You can give yourself water poisoning, not by drinking pure water, I mean, although that too, but by drinking huge amounts of just tap water.
Yeah. Oh man, I know about water poisoning. One of our producers was saying that in college, they would even try to get drunk on water, which is, by the way, a terrible idea. If you drink too much water, even like water that does have minerals in it, you get confused.
Hallucinate?
You hallucinate. I looked up the LD50 of water.
Go on.
The LD50 is the dosage of anything all at once that causes 50% of a test population to die. And in rats, poor waterlogged rats, it's 90,000 milligrams per kilogram of body mass.
Sorry, 90,000 milligrams of water
per kilogram
of mass.
Body mass.
90,000 milligrams. Oh God, can you not just give me in kilos?
Yeah, okay. 90 grams of water per kilogram of body mass in rats, which like a lab rat doesn't even weigh a kilo. So
like half a kilo maybe.
Like what? Yeah.
So 40 grams of water could kill a rat, or give a 50% chance of killing a rat.
A 50% chance of killing a rat if you gave them 40 grams of water right away.
Nothing.
Isn't that incredible?
That's like a double shot.
Sorry, rats.
I mean, I guess when you think about it, if you have a rat, like a pet rat, and when they drink water, they drink like literally a drop at a time.
That's right. Yeah, they're drinking like a gram at a time, and then they're done for a while.
That's not very much, though. Still,
it's not very much. No, I mean, our bodies have this very fragile balance of homeostasis where we're healthy.
Hold on,
just like a rat does.
Let me work it out for a human. So, what was that? 90 grams per kilogram.
Yeah,
7 kilos of water, basically.
7 kilos of water. That's because how much water weighs a kilo?
1,000. It's the same, right?
It's a liter.
1 gram. So 7 liters of water. Oh, 7 liters of water is a lot, though, actually.
Because as I was looking into actual cases of water poisoning, there was someone who drank 6 liters of water in 3 hours and died.
Yeah.
So that kind of makes sense. 3 hours is a long period of time, though, compared to LD50 usually means immediately. Like you give it all at once. You couldn't probably put 6 or 7 liters of water into someone right away.
And the way that this kills you is that, I mean, it's the same as if you drink pure water, right? It's that you have these minerals in your body that are actually extremely important to the function of your cells. And because you are putting through effectively a solvent through your system, it's stripping away those minerals and ejecting them from your body and robbing your body of the things that it needs to function.
That's right. Yeah, your blood and your tissues, they've all got a much higher concentration of dissolved solids than water does. So you water your body down, you lose those electrolytes, and you can die. 6 or 7 liters in 3 hours will do it.
My mum once gave herself water poisoning She was in hospital and she had a kidney infection. She'd been in for pneumonia, and the doctor said to her, "Just make sure you drink lots of water." And she's Irish and really has an unhealthy respect for authority. And so she took it very, very, very literally. And I don't know how much she drank, but my goodness me, it was awful.
What happened?
She just for a few days, I think she basically induced the same effect that our producer intended as a student. Don't do it to yourselves though, because you also, I mean, people, as you say, right, you genuinely can die from this.
You genuinely can. And it's, I think, underappreciated how dangerous it is. There are a lot of like hazing rituals that involve making people chug a bunch of water, and then they'll wind up having to go to the hospital because they're intoxicated with water. Their bodies, their brains, their cognition, it's all hampered by this electrolyte imbalance induced by drinking too much water.
You know, I went to Singapore to go and talk to them about their water system. And in Singapore, they have you wouldn't think it because it's, where it is in the world, it rains all the time, but it's extremely water scarce, right? They have real critical issues about the amount of water they have because they've got very small land area and a really high population of people. So what they do in Singapore is they take raw sewage and they process it through a plant, and then immediately with the output of that system, put that purified distilled water back into the taps, right?
So, just like the International Space Station.
Just like the International Space Station, exactly.
Yesterday's coffee is today's coffee.
I, luckily didn't have to be there for the sewage part, but it was effectively drinking water that morning had been sewage.
Wow.
Just tasted like water, to be honest with you.
Of course, yeah.
But the thing is, the water they create ends up being so pure, right? So stripped of minerals, they don't actually even use it for drinking water. Instead, they sell it to places that are making semiconductors and electrical equipment who need that purer water.
So every time you flush, you're helping technology.
Helping technology. That's what they say in the ISS.
That's really good to know. When you look at Earth from the outside, it is covered in water.
70% or so.
70% of its surface is just covered in water. But Earth's surface is nothing compared to its inside, especially because it's a sphere. Smallest surface area to volume ratio. And I once did this calculation that if you scaled the Earth down to be just 30 centimeters across, like a foot across, like a typical classroom globe, the total amount of water on there would be just under a tablespoon, 14 milliliters. So imagine like a little less than a tablespoon of water, throw that on a globe in a classroom. That's all the water that fills all the oceans because they're just not that deep compared to Earth's radius.
Well, I guess if you think about it, it's like the distance between the top of Mount Everest to the bottom of the Mariana Trench is 13 kilometers, something like that?
Yeah.
Roughly. And yet the Earth is 40,000 kilometers in circumference. So we're talking about, it's unimaginably smooth. And it's just, I guess, with surface tension on the globe in the classroom, you can't.
Yeah, how would you do this at that scale? You'd somehow need to get about a tablespoon of water on the globe. So it would just kind of be like a damp globe. A giant that could hold our Earth wouldn't be like, oh, it's soaking wet. It'd be like,
a tiny bit sleepy.
Brush it off. Yeah. Oh, it's got a little dew on it.
You could imagine doing it with something that had a different viscosity, right? Like some different fluid properties.
True.
You could it's almost like you put a polish.
That's right. You could take
it.
14 milliliters, a little less than a tablespoon of honey, and smear that onto a globe and say, that's it. That's all the water, period. Am I including groundwater and stuff here? I think in those figures I was including all types, even the water in the atmosphere.
But then of that, the 14 milliliters, it's, what was it? 0.0?
Yeah. As an American would say, 0.0076% of all of Earth's water is surface, liquid,
drinkable,
fresh water.
Which means the water we're drinking, / coffee, has been through many, many animals, creatures in the past. Almost certainly we're drinking dinosaur pee.
Oh, almost certainly. Yeah, that whole thing about every breath you take contains some atoms that Julius Caesar breathed in.
Here's the thing that I like to think, right? In our evolutionary past, we started off in the water, and then there was one point where, started laying eggs on land and kind of eventually evolved into creatures that could live predominantly on land. We didn't leave the water behind us. All we did was we just turned ourselves into water balloons and carried it with us as we go.
That's right, isn't it?
And as you're, drinking your drink during the day, what you're doing is you're just topping up the evaporation that you're
That's
experiencing.
Right. We like to call ourselves land animals, but really we're water balloons. In fact, the first living things to move on to land would do it, but then they'd go back into the water to lay their eggs. But there was a major evolutionary step where animals evolved that laid their eggs on land. And they needed to have a hard shell for that so that the water wouldn't all evaporate away.
Exactly.
They needed to evolve water balloon reproduction organs, and they did. And that's still what we do today. We're moisturizing, we are drinking water, we're eating water in our foods, and we just don't really belong up here still.
This is the reason why you weigh less in the morning. Do you know this?
Yes,
So you are literally evaporating overnight.
Yeah. Yeah, you weigh less in the morning because you're losing water, and you know how you're losing it, right?
As you're breathing,
As
it's
you're
all coming
breathing
out.
it out. Your hot, moist breath is just like a weight loss secret.
If you just carried on like that, you would eventually end up as a raisin.
Yeah, you would. The land is just a raisin factory, and we are temporary tourists up here.
Are there any liquids that aren't predominantly water, though?
Yeah, that's what I was just thinking about.
Well, honey, okay, sure.
Honey is liquid-like.
I want more, though. I want more than 18%. I want something that is not water at all.
Yeah, so let's look at things that are liquid at room temperature and pressure on Earth. So, okay, mercury.
Can't drink it. Not interested.
Can't drink it. Bromine.
Can't
drink it. Alcohols and oils.
But alcohols, if you're talking 100% pure alcohols, ethanol, methanol, whatever
Which
it
is
might
pretty
be,
hard to make.
pretty hard to make, but also don't drink it.
Don't drink it. And you could drink like olive oil.
Surely there's still some water in olive oil.
Olive oil contains about 0.03% water.
Wow. Which is very small.
It's very small. It almost seems like you could find that much water in anything, even like in, pure gasoline.
Yeah.
There's going to be a little bit of like moisture just from the humidity of the environment.
What about glycerin, actually?
Glycerin. You could drink that, right?
I reckon. It probably
What
wouldn't
would
be very
happen
nice.
if you did?
Probably pass through. I mean, once you start categorizing things, then we're basically down to everything is either olive oil or dinosaur pee.
Yeah, as it should be.
As it should be.
And I'm glad for it. I was once looking up the etymology of the word loser.
Right.
Don't ask me why. But as it turns out, to be a loser is the same as to be dissolved.
Is it?
Dissolving, solution, loser.
No.
These words all come from the same observed phenomenon, which is dissolving, to be lost in water.
And so lose from the same etymology?
When you put water or minerals into water, they get lost.
Right.
They dissolve.
Because you can't see them anymore.
You can't see them anymore. And when you work on a math problem or just a problem in your own life, what you're looking for is a solution, a circumstance in which the problem, just like minerals in water, dissolves and it goes away and it's no longer visible.
I love that.
Isn't that beautiful? So,
But then wait, what are you losing? What's the
what is dissolving away and disappearing? I guess your opportunity to be a winner is now gone.
Yeah.
Maybe you've lost the respect of the spectators or something, but
Yourself.
Yeah.
Family.
But if it wasn't for losers, we wouldn't be here. We need dissolved solids in water.
I mean, there is, as I have very much come to the conclusion over the last half an hour, nothing more important than this particular loser here, this jug of largely H2O and a lot of other stuff.
Exactly. Yeah. Life depends on that loser. We're all losers in a way. You and I are losers, and you are a loser that we love very much. If you've had fun, follow us on wherever you listen to podcasts. If you're watching on YouTube, leave a comment, subscribe, give us a favorite. What else does YouTube offer? Can you do favorites anymore? Oh, I'm really dating myself here. As always, you can email us at therestiscience@goalhanger.com. Thank you.
Thank you so much for listening. We'll see you next time.